So hi everyone. So today we're very happy to have Chen-Hsuan from MDI Research to join us as the speaker of our first in-person seminar event since the pandemic. And Chen-Hsuan got his PhD and master's in robotics from Carnegie Mellon University. And his research has been focusing on combining classic vision algorithms, in particular like geometric methods, with modern deep learning approaches. And with these tools, he's able to design a lot of very efficient and effective methods. And he's able to exploit the structure in the data and build really great models. And Chen-Hsuan in the past have done a lot of amazing work in 3D, which also won him the NVIDIA Graduate Fellowship in 2019. And today, I believe Chen-Hsuan is going to tell us all about those cool work. So that's welcome, Chen-Hsuan.
Yeah, thank you, Wei-Chu. Thanks for the very generous introduction. So I'm Chen-Hsuan, and I just got my PhD from CMU around a couple of months ago, and I just started at NVIDIA around a month ago. But most of the work I will be talking about today will be around the work I've done in CMU. So really nothing about, from NVIDIA, but it's mostly from academic work. So so if anyone has any questions, please feel free to interrupt, or you can do the questions to the end. It's fine, both fine with me. All right. So okay, let's see. Okay, so consider this very beautiful photograph, and when we look at this photograph, we can immediately recognize this as the Coliseum in Rome. But we might think about how do we actually do it when we just look at this single photograph. So if we show this photo to a machine or AI system, it will probably just treat this kind of image as 2D pixel grids and just process it with a standard machine learning model like 2D ConvNet, or maybe more recently vision transformers. But in either case, it will just treat this as 2D pixel grids and use a neural network to process it, and then encode it into some high-level features to do some certain tasks. But that's not really how we as humans really see these images. When we look at this photograph, we are able to identify there's underlying geometric structures. For example, this has an oval architecture with arcades regularly spaced out at regular intervals. And this is because we have this natural ability of seeing this photograph in 3D. We're able to perceive this world in 3D when we see images. And we naturally picture a mental model of what the 3D structure would look like. And we can do so with pure vision without really having to touch or feel what the Colosseum is physically. And in addition, we can also infer the corresponding location or the viewpoint point relative to the 3D model that we just built in our minds. So we can actually infer where we are actually looking at from the reconstruction that we have mentally in our minds here. And so this regards two important problems in this space. So the first problem is obviously reconstruction. So we ask how do we reconstruct this 3D structures or geometric structures from this photograph? And also the other very important problem is registration, which is where we need to figure out how the images are aligned to the 3D structures or the 3D reconstruction that we built, that we picture in our minds here. And the problems of registration and reconstruction are very tightly coupled together, because if we want to have a very good 3D reconstruction, we need to have a very high quality registration of the images. You can think of it as camera poses in a sense. So we might need to really know what the accurate camera poses are, so that we're able to build good reconstruction. But on the other hand, if we want to solve for a good registration, we also need to have high quality reconstruction as well. So you can think of it as tasks of camera localization, or maybe post-estimation, where we typically will have some predefined or a given 3D models, and then we solve for what the corresponding camera poses are with respect to the images. So these problems of registration and reconstruction are very tightly coupled together, but I think in the community right now, most people are mostly more focused on the problem of reconstruction. And there are not too many people in the deep learning era that's really thinking about that much about registration. So these problems are pretty tightly coupled together. And so if we want to kind of use some learning methods to learn registration and reconstruction, we will also need to have maybe a large image data set or video data set with some so that we can kind of solve for these corresponding with some correct poses so that we can solve for this 3D structure altogether. And this kind of so these problems considers very important applications of, for example, for autonomous driving, robot navigation, computer graphics, and AR, VR, or maybe more recently mixed reality, and also to medical imaging. So this kind of problem is kind of very general, but it also considers very major applications nowadays. And so my kind of interest in this, so this is actually still a very wide and general space here. But my research is more focused on how we can learn this kind of concept of registration and reconstruction by looking at just from a lot of the images and videos that we see. So if we look at all these photographs, you can see that you're able to now reconstruct these kind of 3D structures of not only the Colosseum, but also all these famous landmarks like pyramids and bars. When we only see these kind of photographs, we can kind of picture what the 3D structure actually looks like. And also we also see a lot of videos in our everyday lives. For example, you can look around and we're able to kind of infer what the 3D structure look like, what the 3D structure looks like, without really having to really been there or having to touch or feel. We kind of learn to develop this kind of ability just by looking at a lot of the images and videos we see from birth to our everyday lives. So we as humans learn to develop this kind of ability, this kind of dense 3D perception ability, just by looking at a lot of these images and videos that we see. So my kind of long-term research is more focused on I wanted to answer the question, can we also allow machines to do the same? Can we also kind of enable AI system to learn to perceive these kind of dense geometric structures from abundant sources of visual data like images and videos? So this concerns some pretty important 3D vision tasks, which we can kind of classify in a high level as follows. So the general problem of registration is related to vision tasks such as 6-stop post-estimation, where given that we have some 3D models, we want to kind of estimate what the corresponding camera poses are relative to the images. And also one of the other examples is camera localization, where given that we have a street scene, we want to figure out where we are, where the vehicle or the agent is corresponding to a given map. And the problem of reconstruction concerns some tasks like 3D shape prediction. For example, given that we have an image, we want to kind of predict what the 3D shape looks like from a single image. And also more recently, we have a new type of view synthesis problems, where given that we have multiple view images, we want to kind of figure out how we can synthesize these realistic novel views from these novel viewpoints given a set of different images, and then how we can also extract out these underlying geometric structures from these multiple images. And we also have this joint problem of to solve for registration and reconstruction at the same time. This is classically one of the classes are classically known as structure for motion, where we kind of given that we have set of images without knowing the camera poses beforehand, we want to jointly solve for the 3D structures and the camera poses all together. And also the problem of SLAM, which is simultaneous localization and mapping, which is basically an online version of real-time. You can think of it like the real-time online structure for motion method, where we solve for the mapping and the camera poses on the fly. So these are classical vision tasks. But my research is focused on how we can do this using a learning-based methods to do this for to solve for dense geometric structures, because as you can see from structure for motion and SLAM methods, the natural output of these methods give us sparse output point clouds. But we know that this is not really what the world really consists of. So my research is more focused on how we can extract dense geometric 3D structures from from images and videos here. So just to give a very brief overview of what my research has been doing on about, my older works in my PhD has been more focused on like dense image-based registration or direct registration using in different aspects, such as like structured optimization or using registration for downstream like discriminative task or like or in a general setting. And also I've been working on some aspects on like dense reconstruction where we can kind of like think about like different settings where we can learn these 3D shape predictions given that we have like multi-view or single view images, so that we can kind of learn a neural network to predict these 3D shapes. And then at the intersection, I've worked on these different aspects of how we can use these like shape prediction methods to further utilize them to make them align to like test videos during test time, where we can kind of like align the shapes to the given videos, so that we can have these like shapes like accurately aligned to the given videos. And also more recently, we have a work on like learning in representations from like unknown camera poses, where given that we have like a randomly initialized like camera pose or like initialized at the identity, we can kind of like jointly solve for this scene representation and the camera poses all together by utilizing this like more generic rendering prior. So today I'll be talking mostly on the work of my later works on like reconstruction. So first I will be talking about how we can learn a model to reconstruct 3D shapes that's only been trained on static image collections without multi-view, like without any kind of like 3D CAM model annotations or like multi-view observations. And then I will talk about how we can use these shape priors to kind of like register them and refine it to the given input videos. And then how we can go beyond these shape priors to use like a more generic rendering prior to solve for general things in the camera poses altogether. Just take a sip of water too. Okay, so consider that like if we look at this kind of image collection of objects that belongs to the same classes, and even though we have never really looked at the same object twice, we still have a kind of like good sense of what types of 3D shapes and variations to expect from the object categories. So for example, so we like see a lot of different cars. And so we want to ask the question, like, can AI models learn to reconstruct the 3D shapes by just looking at like a collection of single static images as the training data, and potentially with some kind of like more scalable or practical annotations here, and in this case, like from single images. And so our goal is to learn this kind of like a neural network that can predict a 3D shape that goes from an image to a 3D shape. And this shape is kind of like will be typically be parameterized by some kind of like neural network models. And the most straightforward way of training this kind of network is to directly supervise it with the corresponding 3D CAM model. For example, we have like 3D CAM model to learn this kind of model here. But the amount of image data that we have and the CAM model that we can annotate is not really like scalable, because we might have a large data set of images, but it's really tedious and laborious to annotate all these CAM models to the images here. And in a lot of cases, we don't really even know what the corresponding underlying CAM model is with respect to the training images. So we want to ask the question: can we get rid of this kind of direct 3D supervision, and how can we utilize some more practical annotations to learn these kind of 3D shape predictions? So one of the core components that really connects these 3D shapes to 2D images is the rendering operations. So basically, how it basically simulates like how we see the image, how do we see the visual world of the facing structures. And if we want to learn this kind of model end-to-end, we will have to have some other ways of making this rendering operation, which is classically non-differentiable, to make it like differentiable, so that the gradients can be propagated for end-to-end learning. So differentiable neural rendering has a recent surge in the last couple of years for these kind of like 3D reconstruction and also view synthesis applications. And there has been different neural or differential rendering methods that's been designed for different 3D representations as well. For example, like point clouds, meshes, or voxel grids, and also like more recently like implicit representations. So this kind of like differentiable or neural rendering method is one of the key components that allows us to connect these shape predictions to the image space, so that we can learn without these direct supervision. And also, we also can make the assumption that if we are considering mostly like object categories, we can assume that these object silhouettes that can be annotated are available as well. And silhouettes contain like very rich information about the possible 3D shapes that an image can take on. And it also dates back to some of these more classical works of visual Hall and space carving as well. And silhouettes can be very cheap to annotate. And also there are also like semi-automatic labeling tools out there that allow us to kind of like automatically find like what the roughly annotation is, so that this kind of like annotation process of these silhouettes can be very scalable. And this is kind of like makes it a very practical source of supervision as well. Now, a very common setting of doing this, like learning from these silhouette annotations, is to assume that we have multi-view observations of a single object instance as well in the training set. So this is commonly inferred as like referred to as like multi-view supervision, where we assume that given that we have an object instance, we have like multi-view observations as well as their silhouettes available during the training set, so that we can learn from these like multi-view images and silhouettes during training time to learn this kind of like 3D prediction model here. But this is still kind of like impractical, because it's not as impractical to annotate multi-view silhouettes in contrast to like just annotating like a single image. And for this kind of reason, most of the experiments today using this kind of method are still limited to synthetic data. For example, like ShapeNet, because it's still kind of like not hard to like scale these kind of annotations to real world images. And you can imagine that if you want to like annotate like a real world video, you will have to annotate every frame of the corresponding object, and that's still kind of like tedious. And so what we do here is that we want to still make it even more scalable, and we can allow the kind of like 3D prediction model to be learnable from single view supervision. So given that we have each image, we only need like a single observation of each object instance that's being looked once, and as well as its silhouette. And if we can do this, we can start to learn from these more abundant sources of like static world images, and also annotating these kind of single view silhouettes is a lot more scalable, and we can start learning them from like real world data, for example, like ImageNet. And we also use like sign distance functions as the 3D representation to represent what the 3D shapes looks like, where for each input 3D coordinate x, the output will give us like the distance to that point, of that point to the shape surface here. So this kind of implicitly encodes the surface as the zero level set of a function f here. And sign distance function has the power of modeling the smooth and continuous function surfaces. And we also have this kind of flexibility of modeling arbitrary shape topologies that we might encounter in the wild. So this kind of like 3D shape, 3D shapes will be represented by these parameters of the SDF here. So the network will basically try to predict what the parameters of the SDF that models the function f here. So the neural network here basically acts like more like a hyper network. And so this kind of like gives like a very smooth and continuous representation of the surfaces, and allows us to model like arbitrary shape topologies. And one of the like more pioneering work in this space is the work from Kanazawa et al., where it basically tries to predict like these kind of 3D shapes for single images using 3D meshes. But meshes has these inherent limitations of being discretized 3D representations, and as well as having to be confined to like a predefined shape topology here. So meshes has the like inherent representations, and SDF is a lot more flexible in this case, in this sense. So now we want to think about how we can connect these kind of like SDF shape predictions to these silhouettes that we have, and how we can use these silhouettes to supervise, intersupervise what our 3D shape prediction would look like. So we want to think about what's the connection between these two here. So consider this like very simple image of a Stanford bunny and its silhouette here. So consider that we have this like 2D pixel coordinate that's we write as U here. We can basically each shoot array to the 3D space here, and sample a 3D point along the array, which we at depth z here, and we write as like homogeneous coordinate here, what the that we want to predict. And so what we can do here is that basically we can first compute like the distance of this to the coordinate u here to the silhouette, and this can be done by computing the distance transform of each pixel. And based on this, we can basically draw this kind of circle around this 2D coordinate, and we can see that this is guaranteed to be all free space by the distance transform. So the entire region within the circle is guaranteed to be a free space. And then correspondingly, when we back project this circle into the 3D space, this entire space of the 3D space of the cone here will also be guaranteed to be free space. Right. So given that we have this pixel coordinate u and also the 3D point here, we have this kind of like we can write a relationship between what the 3D SDF, the value this particular point can take on, as like a function which is basically the distance to the conic surface. And this has like a deterministic expression here, which we would just express as like a B function. But the point here is that this is always going to be bounded, and so this can serve as like a lower bound on what the SDF value it can take on. So we can use this as like a supervisory signal to say like what the actual 3D SDF value it can take on. So a valid 3D SDF shape should satisfy this kind of like inequality everywhere in order to be a valid SDF shape here. So we can basically write this constraint and using like a maximizer loss function. So basically, if the value is less than this kind of like this is lower bound, then we impose a loss here, or otherwise we just like ignore it. So this is basically like a maximizer loss function, and we do so for all the sample pixels in the images here, and also for all these randomly sampled depth. So basically, we want to try to constrain it for all the 3D points that's being sampled in the 3D space here. So this is basically like the SDF loss function that we imposed here. But if we look at it more closely, you can see that this is basically still an under constrained loss function itself, because we can always find a trivial solution where a large SDF value can be predicted everywhere, and it would just still give us like a trivial solution of like a zero of a null shape, and it would still satisfy this kind of like zero SDF loss. But we want to we make the observation that if we kind of render for the interior pixels within the silhouettes, it's always going to cross the zero intersection of the SDF shape here, because this is how the scientist function shapes are defined here. So we can use this as like a additional constraint by trying to render the pixels that's within the silhouettes here. So typically how we render the pixel of the silhouette is that we can use like some kind of like ray marching algorithm, or we're using like sphere tracing to kind of like render what the zero crossing, what the color of the pixels is at the zero crossing of the SDF shape here. So we impose this as like a regularization where we enforce that the endpoint of the ray tracing should be always predict the zero level set. So this is like an additional loss we can impose here, but we use like a version of the of a differential version of this ray marching algorithm called differential ray marching, which is a really nice work from Vincent Spent here. And this is actually allows us to make this like rendering operation differentiable by enrolling it with a new recurrent neural network here. And so this allows us to learn this kind of like rendering operation end-to-end for a neural network. And what we do here is basically we impose like a very simple L2 loss here on the pixel intensities here. And it looks like it's like really simple, but what we found here is that this is also actually very sufficient to allow us to find this kind of like these correspondences between like within a training set, even from single view viewpoints. And this actually allows us to use the appearance by rendering the appearance. We can help resolve these kind of like shape ambiguities that we will have between these like object instances. And we found that this allows us to learn even from single viewpoints. And in the next example, I will briefly talk about like a toy example, like how this kind of like works. So suppose that we have like different cars looking into these different viewpoints in the same canonical space, and we're kind of interested in like rendering this like left headlight of the car. And now because the rendering operation renderer kind of like marches away from the camera center and towards kind of like the canonical space that we hear, this kind of like ray marching algorithm marches away from the image plane toward the center, and we'll kind of like discover this kind of like correspondences in the semantic space here without really having without kind of like even though it can't find the exact like 3D point correspondence, it will still be able to discover what the correspondences are semantically most similar to each other. So we can pose this as like a form of like semantic multiview supervision of different images here. So this is like another way of thinking about this problem. And we found that this is actually enough that allow us to learn from a single view supervision, even in the absence of multi-view observations that we have in the training set. So I'll quickly go over some of the results here, and we can see that how this kind of like semantic correspondence association within the training set can help us learn these kind of like phase shift predictions from a single view images.
One question here. So I see there are like different cars in different places. So how do you know like how they're aligned? Like do you have the car pose somehow attached to it?
So we do assume that we know the camera process that's looking into this thing canonical space here. So that is kind of assumed to be known. Yeah. Okay, so we can quickly look at the results here. So first of all, we benchmark on ShapeNet 3D reconstruction. Basically, we have this multi-image and we have this ground truth here. We compare against different baselines. The first one is called soft flash, which basically it relies on multi-view supervision to learn to reconstruct these shapes, and also it uses mesh density representation. So this is our first baseline. We also have another baseline that also relies on multi-view supervision called differentiable one-vector rendering, but it tries to reconstruct implicit surfaces instead. And then we have our method called SDF-SRN, which can learn from single view supervision using implicit surfaces. And we only consider the case of where we use only single view supervision in the training set here. So when we look at how these different baselines reconstruct the shapes here, we can see that if we look look from the same viewpoint as the input image, we can see that the 3D shape actually looks kind of reasonable and fits well to the 2D silhouettes. But if we rotate it around and look at it from different viewpoint, we can see that it kind of drastically, the quality actually drastically degrades. It doesn't really look reasonable at all. Whereas for our method, we can see that by trying to learning these semantic association of these correspondences, we can actually learn to implicitly associate these correspondences and learn what a more reasonable 3D shape should look like. So we can look at some of these results in a category setting where we have tried to like reconstruct these chairs. We can see that on our method reconstruct these shapes that's a lot more closer to the ground truth. And also like different categories, like for example, like airplanes. We can see that for these different baselines, there's also like kind of like different scales of ambiguities that cannot be resolved, because they kind of basically relies on multi-view supervision. And also we can have some results for cars. We can see that our methods can learn to like reconstruct these trucks and racing cars a lot more realistically with higher quality. And now, let's take a look at this more challenging scenario where we learn from real-world images and where we consider the Pascal data sets, and we compare against a baseline called category mesh reconstruction, where it basically can learn from single view supervision, but uses meshes as the representation instead. So we can take a look at how we perform in the test set. So we can learn. Okay, we can see that meshes has the inherent limitation of having to be confined to like fixed topology, whereas our method can reconstruct these like arbitrary like topologies like bars of the chart and also like DDX. And also we can look at some of these more other categories, for example, like airplanes. So these are all like reconstruction from the test sets. And these are like some examples of the cars. So we can see that like our method is not really able to like reconstruct perfect shapes because we don't really have like instance level multiview supervision, but it's still able to kind of like learn a reasonable prior for reconstructing these 3D shapes. And also like quantitatively, we can see that our method is like much better in all aspects with respect to the like when measuring like using the chamfer distance. Okay, so this is like so now we kind of like saw how we can kind of like learn 3D shape prediction from like single static image collections, but when we kind of like look at the results, we can see that it doesn't still look like reasonable to like what we would expect from the input images, and you can see that there's still like kind of like this difference here. It's not really like perfectly aligned to what we would really expect from the images here. And this is partly because these kind of feed-forward predictions from feed-forward neural network models doesn't really directly respect the input observations. And so we want to like think about how can we kind of like use these like pre-trained networks or learned networks as some kind of like learned priors to so that we can further refine these 3D shapes to register them to like the input images so that we can be more realistically, more accurately aligned. Yes.
I've noticed this artifact on a couple of your results. It seems like you kind of have grids outside.
Yes.
Do you know what that comes from?
So that partly comes from like the use of where we use. So we added like this kind of like position encoding component that I'll talk about later. But when we add this kind of like position encoding component that encourages like high frequency, it also kind of like it will also kind of like encourages like some of these like high frequency artifacts as well, where if we don't have like enough trained data to, so this is kind of comes from the use of like sinusoidal based functions in the neural network models here. Okay, so what we can do here is that we can also still during test time we can use like differentiable rendering or neural rendering to predict what the 3D shape will look like. And then basically just use the test image as to directly optimize how the shapes would align to during test time. And so test time optimization helps further refine and register these kind of like 3D shapes to the 2D images. And this has been explored in a couple of different works, and this has been found to be very useful to improve the quality of these 3D shape predictions. But in reality, there are many cases that we see that we really live in like a temporal world, and for a lot of applications like robot navigations, we really have access to these like temporal information where we kind of like navigate around the world. And so we have like these like temporal information not only just from a single images, but also from multiple viewpoints that we can utilize. So we can look around from different perspectives, and we can see how we can use these kind of like temporal information to utilize and further refine these like 3D shapes here. So given that we have like a video sequence here, basically what we can do here is that assuming that we have these pre-computed camera poses here, we can render these 3D shape predictions to different viewpoints of the video sequences here, so that as the video sequence goes on, we can render them 3D shapes at different perspectives and jointly optimize them using all the frames of the video sequences here. So we can optimize these 3D shapes for this kind of like multi-view consistency, multi-view photometric consistency, and what we found here is that this can be done using only photometric information, and we don't really actually need these object silhouettes anymore. We only really need these like video frames in order to achieve this kind of multi-view consistency to align these 3D shapes here.
So how do you estimate like the total score?
So this is in the next slide, and so we assume that given that we have like this object, we can basically pre-compute these counter processes using like off-the-shelf structure motion methods. And so this is like basically our recent work has been doing. Basically treat this like structure motion methods as like a off-the-shelf black box post-estimation method. So we can assume that this is known. And so we consider like this pair of images from the video sequences called I1 and I2, and we know the corresponding camera process as well. And in this case, in this work, we will mostly consider like 3D meshes and for simplicity. Although I'll show later on that the same concept of this kind of photometric optimization can be applied to like more recent like sign distance function as well. But in this case, we will just like mostly consider like 3D meshes for simplicity. So what we can do here is that given that we have this 3D point that's being sampled on the mesh surface, which we call Y here, we can write this point Y as like a convex combination of the mesh vertices here. Yeah. Okay. So we can write this as like a convex combination of the mesh vertices, which we write as P here. And what we can do here is that we can basically project this Y point here to the image plane here, which we call X. And then we can basically just like compare what the photometric differences is at the sample point here. So we use this as basically like a loss function that compares between like the different sample points at different image frames here. So this can be obtained by differentiable sampling, and it's like naturally differentiable. And so we can basically expand this equation out here to rewrite this as like a function of the 3D point, which is in turn like another function of the mesh vertices. So we can use like photometric loss function to basically refine what the mesh vertices P here, so that P can be deformed and make it more aligned. And if we do this for all the 3D points that's being sampled on all the meshes here, we can basically deform the entire 3D shapes because we are basically moving around all the triangles on the 3D shapes. And so, what we can do here is that when we compare two frames at different camera poses, there are chances are that we will have to handle like a lot of these like self-occlusions that's been going on when we look at from different perspectives. So consider that this like particular yellow triangle that's being rasterized here. Different colors basically mean like different mesh indices here. So we consider this like yellow triangle here. If we consider that these two different pairs that's being sampled at the same 3D coordinates, we can see that the red point actually falls when we kind of like rasterize these different points here. You can see that the red point actually falls on different triangles, but when being like rasterized, while the green point is consistent. So we can kind of like we can take care of these kind of like inconsistency by kind of using this mesh rasterization operation, and we only consider the photometric loss only when the rasterization falls on the consistent triangles like yellow one here. So this is basically how we implicitly handle like self-occlusion. We only really consider correspondences where that lies in the same triangle. And we do this for all the triangles that's being rasterized at different frames. So this kind of like entire mesh optimization process basically becomes like a 2D piecewise image registration problem. So a lot of methods can be dated back to like Lucas canonical like methods, and this can be kind of taken care of using like different methods that's being out there. So this entire 3D mesh optimization problem can be related back to like image alignment. And so in practice, what we do here is that because we're assuming that we have a pre-trained shape prior as with a neural network, what we do here is that we can basically try to define all the triangle measures that's been constrained by this shape prior by kind of optimizing it over in the latent space, and then which is basically like initialized with the like one of the frames with the neural like the pretrained network, and then we basically just like optimize over this like learned latent space with the network weights frozen, and basically how we register the register poses is basically we can try to also backpropagate the gradients to the post latent code, which basically parameterize what the rotation and translation would be in the 3D space. So we basically do like test time optimization of the video sequences using like gradient descent, so that they can basically do like test time gradient descent on the latent code and also like the post codes here. So let's take a look at some simple examples where we have some synthetic sequences that's being rendered without any kind of like silhouette or annotation or anything like that. We only have this kind of video sequences that's been going on. So when we kind of like initialize this, so these are like basically different viewpoints that's being seen from at the different sequences. And if we initialize these kind of 3D meshes as we've seen here, you can see like the pose and the shapes are also kind of like misaligned. But if we run this like photometric optimization process, we can see that it can gradually kind of like deform and fits back to the video sequences without having really to relying on any kind of like silhouette annotations or anything or such, where it also doesn't need like depth information to align. It's only solely operating on these photometric consistency here. So this is basically like a process of what the photometric optimization process looks like from different viewpoints. And this is basically like a line measures that's being aligned to the video sequences. And we can also see that if we can also re-estimate the corresponding textures from the 3D model, from the video sequences to extract out back a 3D CAD model with some pretty nicely textured CAD models here.
Sure. Yeah, why is it possible to optimize the mesh instead of the latent code? Like,
so you mean like free form like optimization on the meshes? Just
yeah.
So what we found here is that if we only optimize the meshes, it makes the problem too under constraint, and the meshes will basically just like degrade and blow up. So this kind of like shape prior is pretty essential to make the deformation well behaved. So like basically it just still looks like maybe like these object categories. Yeah. And so we can look at some of these real world results, videos where we basically have like object centered videos looking around like these chairs. And we can do the same where we basically run this like same pretrained model on by optimizing over the link codes on the pretrained model, so that we can see that these chairs are basically aligned, deformed, and aligned to the video sequences here. You might see that there are some discrepancy between the shapes and the video sequences because in this work we basically tried to utilize this pretrained model on synthetic data, and so there are still like a domain gap between what the synthetic data and the real world data. And so there are still like some discrepancies between the actual deformed model and the actual shapes. But I think this is still like a very pretty nice visualization of like what this kind of like optimization process it can allow us to do. And this is also like a CAD model with the textures re-estimated from the real world video, so that we can get out some of these like pretty nicely textured chairs from the real world sequences. And this is and so there are like some follow-up works that directly utilize like SDF representations from these using the same concept to optimize for like higher quality 3D shapes here. So this is like this kind of like concept is also applicable as well. Okay, so I think we only have 2 minutes, so I'll briefly go over like our latest work. And so we saw that we can utilize like these like pre-trained shape priors to kind of like refine these 3D shapes to the test video sequences during test time. So these are basically what the results that we just saw. But we want to think about like, what if we don't have these kind of prior knowledge of these free shapes that we want to expect? What if we only have like what if we have like just arbitrary scenes and we want to like kind of optimize for what the free structures should look like? So we want to think about the problem of, can we go beyond these like shape priors and use like a more generic prior for 3D so that we can learn jointly optimize for registration and reconstruction at the same time for more general things using like a more generic 3D prior. And so we basically take this like very recent work of Neural Radiance Fields, and I believe like probably everyone has heard of this work. And what NeRF allows us to do is that it basically allows us to synthesize like photorealistic novel views from different things. But at the same time, it's also, for a lot of the cases, it also allows us to extract out this really crisp and high quality depth from these novel synthesis as well. So to quickly go over like what NeRF is about. So basically, given that we have like a image and a camera center here, basically we want to like kind of like learn how we represent this like 3D model here using like a neural network, which is an MLP. And so what we do here is that for each pixel which we write as u here, we basically we can sample like a 3D point along this ray. We feed this into like an MLP as the input 3D coordinate, and then we learn to predict what the color and the volume density is. So this is very simple, like input is 3D coordinate, and we try to predict what the color is, and also the volume density. And we do this like, we density sample all the points along this ray for all the points for this pixel here, so that we can do the same for all the points, and then we predict the colors and the volume densities for all the points. And then what we do here is that we use volume rendering to aggregate the predictions for all the points, and try to use volume rendering to predict, synthesize what the pixel color should look like at this location U here. So volume density, volume rendering basically computes like the color radiance and the volume density along the ray. And this can, and what we found here is that this takes like a very structured prior that basically allow us to like constrain what the representation would look like, so that the 3D scene representation can be interpretable in the 3D sense. And then so what Neural Radiance Field does is that it basically assumes that we have multiple views so that we can basically learn to constrain this with multiple viewpoints. And now like a very secret recipe here of why NeRF can learn photorealistic neural ring is the use of positional encoding. And what positional encoding does is basically it maps like every 3D coordinate to some higher dimensional space that consists of these like sinusoidal basis functions of different frequencies, so that it basically learns how to represent this entire scene using different sinusoidal base functions. So you can think of it as like a deep Fourier series, or in some sense. And so this is like a key recipe of why NeRF can learn like these high frequency details in these like view synthesis. So like as a toy example, you can see that without this kind of positional encoding, you can see that this synthesis lacks like a lot of these details in the Lego sequence. Sorry. Whereas like for if we add positional encoding, we can see that a lot of these details can be recovered. Okay, so what we do here is basically we form the optimization as like a very simple L2 loss function. We basically try to predict what the synthesized color is with respect to the ground truth. And so we basically would write this as like a render RGB image, and which is a function of the camera pose and also like a neural network parameters, and we want to optimize what the parameters are here. And so, but we want to ask the question like, NeRF actually assumes that we have to know like very accurate camera poses, but what if these kind of like camera poses are unknown, or even like, or kind of like noisy? When we don't have like very perfect camera poses that's assumed to be given. So we want to kind of like think about, can we also optimize these camera poses altogether with different network parameters using the same loss functions? So this is basically the optimization, the more ideal optimization function that we want to use. But can we just optimize this kind of process naively through backpropagation? And so what we found here is that the answer is not really. And I think it's, I'll quickly go over this kind of details because it's a little bit technical. But what we found here is that basically, if we think about like image alignment or like signal alignment using like coordinate with coordinate-based signals, it's a lot harder to align like signals with high frequency or noisy or like high frequency details basically using just like these signal, like comparing these signal differences. So it's a lot harder to align high frequency signals than to align like smoother signals. So in a lot of these like alignment literature, it's basically very common to use like a smoother versions of signals to do like geometric alignment to align signals together. So we apply this kind of like a concept into this like in NeRF as well. So basically, I'll kind of skip through this kind of like equations, and basically we say that because we found that like this kind of position encoding actually encourages high frequency details. So we kind of like want to regularize how we control how we use these like high frequency details to do like geometric alignment together for NeRF. So basically we can see that for each position encoding component, here the gradient will basically just like blow up because we have this like factor when we derive the gradient expressions here. So for this kind of signal, we will just like scale up the magnitude, and for this high frequency details, the gradient will be like very noisy, and it's going to be detrimental to geometric alignment. And so in practice, what we do here is that basically we try to control the position encoding so that by applying like a real value weight from 0 to 1 to which we write as W here to control what the frequency signals can pass through the MLP for geometric alignment. So at the initial stage during the optimization process, we basically only allow the lower frequency signals to go through the MLPs. And as the optimization process goes on, we gradually activate the higher and higher frequency signals one by one. So these are examples. And as the optimization goes on, we basically just gradually activate all the rest of the frequency signals from low to high. And so this helps this kind of align process a lot. And we call this BARF, which is called bundle adjustment neural radiance fields. And this is like a very nice joint work with Wei Chu and Antonio, which basically says that for this kind of like course-defined optimization process, for this kind of like alignment process, course-defined is like a very essential key component to making the signals register in one go. So this is like a very crucial for joint registration and reconstruction. Oh, sorry. I think. Okay. So here, so we can look at some of these examples, like where we can try to align these like different image patches all together. So basically, this is like a very toy example where we want to, assuming that we only have these like image patches, we want to try to find what the patches are. We want to kind of try to find a consistent image representation of these images of this guy kitty cat here, and this is like the corresponding ground truth warps here, and we want to like try to discover, want to see like whether we can discover this kind of like image warps and also like a consistent image representation at the same time. So if we compare against like different baselines, like if we look at the case without any kind of position encoding, we can see that it can't really model this like kind of like high frequency scene image representations, but it can kind of like allow us to like learn to roughly the corresponding warps of this kitty cat. But if we only like allow all position encoding all the way down, you can see that it can kind of recover high frequency details, but it can't really kind of learn to discover what the corresponding image warps are. Whereas if we do like coarse-defined registration, then we can recover these high frequency details and also like the corresponding warps at the same time. So this is like a toy example of using images as like a toy showcase. And these are basically what the recovered patches look like. We can look at in the NeRF case where we see where we have like multiple view observations of the same chair here, and these are so the pink cameras basically indicates like the ground truth cameras, and compare against like the baseline where we only have like naive positional encoding, and we initialize the cameras to the same amount of like camera perturbations. You can see that like the red lines indicate the translational error between the ground truth and the initial cameras. So during the optimization process, we can see that BARF is able to like kind of like discover like the corresponding cameras very quickly, and we can see that the baseline is having trouble and gets stuck in local suboptimal solutions. So as like a last example, let's look at some of these like real world things here. We have like given that we have this kind of like video sequence of this like real world thing here, we can see that when we kind of like start from the initial identity camera and kind of like just run the optimization process, we can see that like BARF is able to recover the photorealistic view synthesis as well as the depth. Whereas for the baseline positional encoding, it basically just gets stuck in local solutions. And we can also like compare against like these camera poses that's being pre-computed by COMAP, like from these like structural proposition methods. So basically we can align these like estimated camera poses to the COMAP poses and see how much they align together. And we can see that like these computed poses from BARF and also is very well aligned to these poses that's computed by COMAP. So they highly agree with each other, and which basically indicates like our BARF is able to successfully discover these like underlying camera poses. And we can also see from the normal synthesis results from different things. And so these are basically the RGB view synthesis results as well as the depth. And I'll skip the quantitative results here. It basically just says that our method is much better than the baseline. But I want to show the last slide, which basically says that we can allow like some of these more interesting applications where we just use like our iPhone to do like self-capture sequences. For example, this is like a corner of our kitchen here. So we can, it's very easy to like kind of like just capture sequences from our iPhone and run BARF. So this is like our kitchen, and this is like a corner of our living room. And this is a particularly interesting example where a comment just really fails, but we can also still compute like the corresponding camera poses with BARF. So I think this is like a particularly interesting example. This is like a barfing thing of Jacob, and so this is like BARF for BARF, and so we can allow the like very fun applications to do like non-view synthesis. Yeah, so I've talked about like how we can like learn shape reconstruction from static images, and how we can utilize like these different priors of like shapes and also like rendering priors to recover like dense geometry structures from image video sequences here. And thank you all for coming, and I want to thank everyone that's been covered with me along this way, and I'm happy to take any questions here.